Okay, so we'll get started with today's lecture, which is on heuristic search and the A-star algorithm. And just before getting into the lecture, I'm just including a link here to the search demo. So this has all the different search algorithms that we'll be talking about today. I have a part of my website that's kind of like the assignment, and I'll go through a demo of that at the very end. But in case you wanted to look at that for studying purposes or whatever, I just put the link at the beginning of the slides. So informed or heuristic search. So far we've only been looking at uninformed search. And as a reminder, uninformed search is when you don't have any sort of guesses of where you should go. It's just like an exhaustive search. Let's try absolutely everything. An informed search strategy, as opposed to uninformed, uses some problem-specific knowledge beyond just the problem description itself. So what we're going to do essentially is use some guesses, and we're going to call those guesses heuristics, to guide the search toward the direction of the goal. And you will see in other domains of science that heuristic means something different. So there's almost 100 different definitions of heuristic, depending on, if you're talking about biology or engineering or mathematics or whatever. But for the purposes of heuristic search, the heuristic is the evaluation function that we use as a guess as to sort of what direction we should take in the search. And the ideal use case for heuristics is that it's going to reduce the total number of nodes searched, right? And we'll see some examples of that in our visualization where we can see, oh, the closed list is much smaller than it was with BeFS versus the A-star search algorithm or something like this. And ideally, what that will do is also speed up search times to the goal. And so there is a bit of a trade-off here, right? Because let's say, for example, that our heuristic guess allows us to search half of the nodes to get to the same path. But if calculating that heuristic takes so long that we're searching half the number of nodes per second, then we haven't actually sped up the search, right? So there's a trade-off between how much time it actually saves us, or how many nodes it saves us, versus how much time it saves us, okay? And ideally, your heuristic is going to be very fast computation so that it's going to help you overall. So when we looked before, this is how breadth-first search works, where we start at a particular location in the environment. For example, this yellow starting area down here. So initially, that is the state of the open list, and then we expand outward. So we have no real direction that we're going in. We just sort of expand everywhere until we get to the goal. So the first class of search algorithms that we're going to look at in heuristic search is called best first search. And unfortunately, a lot of these acronyms kind of sound and look the same. So for example, BeFS, breadth first search, that is not best first search, okay? So BeFS, that's my little acronym for best first search. And it's an instance of general tree search. And what it does is we are going to select a node for expansion from the open list based on some evaluation function. That is our heuristic function. That heuristic function, that's not the heuristic function. I'll talk about that in a second. But this evaluation function is f of n. And typically, what we do is we look over the open list and we find the node that has the minimum value of f of n. And this is going to be some sort of measure of distance or a guess towards how close we are to the goal. And so best first is a little misleading because if we knew the actual best node, then we could go straight to the goal. So it's more of a best guess first, right? We don't actually know which is the node that we should go to next, so this is a best guess first. And so best first search algorithms can be implemented with the general tree search using a priority queue. So instead of using a queue or a stack or just a vector, typically a priority queue data structure is a data structure which keeps the minimum value in constant time lookup, right? So a priority queue is going to enable us to get that minimum f of n very, very quickly. Typically, the best performance that you'll see from a priority queue is going to be something like a log n insert time and a constant time retrieval. Okay, so that's sort of the best you can do. Unless you have a very specific instance of maybe if you're working with really small integers, then you could bucket them or have a hash table or something like that. But typically, we want to make this retrieval of f of n and insertion into the priority queue as fast as possible. And there's a whole family of best first search algorithms, and they have different evaluation functions, but what they mostly share in common is that they have a heuristic function, and this is our guess towards what direction we should go in for the search, and this is called h of n. So this heuristic function, at least in the context of our course and our search algorithms, this is an estimate of the cost of the optimal path from any node n to the goal node. So this is a guess. We apply some sort of domain-specific knowledge to say, what do we think is the optimal cost to go from this node to the goal? And the heuristic functions are the most common way that we can provide sort of additional knowledge of a problem into the search algorithm. And so one definition is that if we are at the goal node, this is something we can test, then h of n, which is our guess of how far we have left to go, is 0. So that's always going to be true. If we're at the goal node, oh, I have it on silent, I promise. Turn that off. Phone calls go through my do not disturb, I think. All right, sorry about that. So if n is the goal node, then our guess at how far we have left to go, we are at least smart enough to know that we have no distance left to go. And if we had access to the perfect heuristic function, that would essentially be able to tell us the optimal path cost from this node to the goal. That doesn't exist, obviously, because we have to do search to know the optimal path. But if we did have it, we're calling that h star of n. So let's look at a couple of examples of a heuristic function. So let's say that we are at this node up here, and we're trying to get to this node down here. So hands up if you could tell me what might be an estimate of the optimal distance to go from one of these nodes to the other node. Yep. Yeah. So just like the straight line, right? So the fastest way between 2 points is a straight line. This is a guess at how far we have left to go. Now, obviously, in this case, it's not going to be exactly the optimal cost, right? Because we can see that in a lot of cases, we're going to be going through obstacles or whatever. And also, in our assignments, we can't move at that exact angle. But it's just a guess, right? And for purposes of a heuristic function for our search, this is a fine guess. Now, we will see soon that there are properties of heuristic functions that make them better or worse for our particular algorithm. But this is one of the ways that we can guess the distance remaining, right? So if I had to guess in real life, what is it a shorter path to go from me to that window or from me to the dean's office out there, right? So my guess would be, okay, that seems like it's a bigger distance. Now, I don't know. Maybe there's some weird stuff on the floor that I can't walk around, and I'd have to take this huge long path. But it's just a guess, and one of those guesses is just, let's take the Euclidean distance between 2 points. Another guess would be what's called the Manhattan distance. And it's called the Manhattan distance because if you've ever seen Manhattan or a similarly big city, the city is divided into grids, right? So to get from one building to another building in Manhattan, you sort of have to go over so many avenues and then down so many streets, right? And this happens to match up very, very nicely with our assignments, right? Because we're working in these grid worlds. So the Manhattan distance would just be the sum of the distances, the sum of the differences between the x's and the y's between the start and the goal. So this is another example of a heuristic function. And we can think of a ton of different heuristic functions. Return 0. That's a heuristic function. It's a bad one, right? But it's a heuristic function. Typically, we would want our heuristic function, the guess, to be as close to the optimal path as possible, right? Because that would help us in our search. However, this one right here, this works out really, really well in this case. But in this case, the same heuristic function is not so accurate, right? Because the actual path is much, much longer than that. But it's still a guess. So the first algorithm we'll look at is called greedy best first search. So this is a type of best first search algorithm, and it's just greedy with respect to the heuristic. So this expands the node on the open list that it thinks is closest to the goal node. That's all that it does. So hopefully this will lead us to the goal faster. And so for greedy best first search, our f of n, which is the function that we want to use to select the minimum one from the open list to expand next, that is just equal to h of n. So whatever heuristic we have, we apply it to each node, and we return the minimum heuristic value from the open list. And this is going to somewhat resemble depth first search, because it's basically going to try a single path all the way to the goal and then back up when it hits a dead end. So best first search operates like this. You start here at this node on the left, and you're trying to get to this node on the right. And what you're going to do is apply h of n to all the nodes on the open list. So of course, at first, we only have one node on the open list. So let's pretend that we're using octile movement, so we can move in 8 directions. That's what we're doing for assignment 2. And now what we have to do is we have to evaluate all the nodes on the open list and pick the one that has the minimum value of f of n for this. Oh, sorry, this is my example of breadth first search first. So if this was just breadth first search, we would just search like this until we got to the goal. And look at all the nodes that we would have to expand, right? Almost the entire map. Best first search, and especially greedy best first search, after it expands this one, would look at all of these nodes, and it would say, which one is closest to the goal node, right? Let's just say, for example, we were using the Manhattan distance or the Euclidean distance or whatever, but just some notion of that distance. So it might say, okay, of all of these, this one, I think, is the closest. So that's the one I'm going to expand next, right? Now let's do that again. Okay, so it's this one. And then we keep applying this process until we get something like this, right? And you can see that, yeah, that actually looks like a really good path. And we've expanded far fewer nodes than the breadth first search did, right? So mission accomplished. That was great. However, now, if we look at this example, where we don't have such a great time, we would keep doing this process of selecting the one that's closest to the goal node. But now what happens is, when we reach this structure, we're going to have to evaluate sort of all of these. Because we get here, we go to this one, it thinks this is the closest, then it thinks this is the closest, then this one, then this one, then this one. And we will see, when we do greedy best first search, that these sort of concave structures are like our Achilles heel, right? Because we have to search everything around there before we actually go in a different direction. Because we're going against the heuristic when we go in a different direction, right? So let me just quickly show a little demo of this with my search. So this is the search thing that I was just talking about. And I will go, a good example of this, let me just maximize this, is the caves. So I have, let me go sparse caves, toggle off the grid. And let's say now that I want to go from right here, and I'm going to choose greedy best first search. So I'll go from right, let's say, here to right over here. Now, I know this is a bit small, but you'll be able to see the closed list expanding when I do this. And actually, let me turn on the animated search. So what's going to happen is we're trying to go from right here to right here. And so the Euclidean distance heuristic, or the heuristic, is going to try and take us right into this little cave. And we're going to, unfortunately, have to fill up that entire cave, right, before we can escape this. And so this is an example of, yes, the search is guiding us toward that location, but it's got to fill up all these concave structures. And that's the worst case scenario for these type of heuristics, when the direct path to the goal is sort of not a good path to the goal. But watch this. If I'm right here and I want to go right here, it guides us right toward the goal. So that's a really good case, right? Now, one more little case is if I take, I believe I have some mazes here, like a medium maze, right? So if I want to go from right here to right here, no, that's an easy case. Let's say right here to right here, right? You might have to fill up the whole map, right? It may be no better at all than something like breadth first search, because it's trying to go in the direction, but there's all sorts of walls, and any maze you may have to go all the way around. So sometimes, in this case, it actually did a decent job, but in general, it's not guaranteed to do any better. All right. see if I can remember this hotkey. There we go. So the performance of greedy best first search. It suffers similarly to depth first search. It is incomplete in general. It may not find a goal. It may get lost in weird paths if the heuristic is really bad. And it is certainly not optimal. We actually just saw from those examples where it went in the cave. It actually went into the cave, then out of the cave, then around. And so in general, it's not optimal either. And again, like DFS, the time complexity is big O of b to the power of m, where m is the maximum possible depth of a solution. Whereas BeFS would have b to the d, where d is the first depth of a solution. Okay, so that's greedy best first search. Now let's talk about some properties of heuristic functions. The first property, and the one you'll see by far the most if you read more into this, this is called an admissible heuristic. So an admissible heuristic is one that never overestimates the distance to the goal. So if we have a true distance to the goal, the admissible heuristic will guarantee that I cannot guess something that's bigger than that. Okay? So it's always an optimistic guess, because in terms of path length, lesser is optimistic. And so, yeah, it can be seen as an optimistic guess. So mathematically, h of n, which is our heuristic, has to be less than or equal to h star of n, which is the true heuristic function, or the true cost to the goal. And so what this means is if we have g of n, right, which is the distance that we've come so far to a node, and we add h of n to that, this value will never overestimate the true cost of a path through n when h of n is admissible, right? So if I've come so far, that's g of n, and I have h of n left to go, and I know that h of n will never overestimate, then g of n plus h of n will never overestimate the true cost of that path. And that fact is going to come back in a minute to help us. So let's talk about some heuristic functions. Again, don't shout it out. Put your hand up if you think this is just a poll. It's not saying anything. Put your hand up if you think this is an admissible heuristic. So ask yourself, can this ever overestimate the true cost of the path? Okay, I see a lot of people shaking their heads. So if it can never okay, what's the shortest possible path between 2 points? That. So if that is the shortest possible path between 2 points, can it ever overestimate the actual path? So it can never overestimate. So what is it admissible? Yes. The definition is, right? The definition is it can't overestimate. And if you've defined the shortest possible path, then it can never overestimate. Now, is the Manhattan distance an admissible heuristic? Hand up to explain if you think it is and why or why not. Is anyone brave enough? Because there's a kind of a trick question. Because there's another question you have to ask before you can answer this. Yep?
Because if we can only move in 4 directions, it wouldn't be a shorter path to get.
Okay, so you said the tricky thing, right? Which is, in order to tell if a heuristic is admissible, we have to first consider what are our actual legal actions, right? So if we are only allowed to move in 4 directions, up, down, left, and right, then this is admissible. Because this is going to go through obstacles. It's the shortest possible way, right? But if we can move in 8 directions, then we could do this and cut across this diagonal. In which case, this 4-directional Manhattan distance would not be an admissible heuristic in the context of being able to move in 8 directions. Okay, that's a good exam question. However, if we are allowed to move in 8 directions, and we have a diagonal Manhattan distance heuristic, which is just defined as basically you take the diagonal until you can't anymore, and then you go straight. In the context of 8-directional movement, this is an admissible heuristic. Even in the context of 4 directions, it is an admissible heuristic, right? Because a 4-directional path could never be faster than that, right? And so if this can never be more, then it's an admissible heuristic. So you have to ask yourself, what are the legal actions first? But If we are able to walk in an arbitrary line straight toward the goal, then this is no longer an admissible heuristic, right? It has to do with the actions that are legal. For assignment 2, and going forward, we're going to assume that we're talking about octile distance in a grid. Okay, so yes, this is an admissible heuristic for that. Okay, now we're going to introduce the A-star search algorithm. And I could have introduced the A-star search algorithm on the second lecture of class and just given you the algorithm, and you would have memorized it, and you would have regurgitated it, just like I did when I took the AI class that I took many years ago, right? But I had implemented the A-star search algorithm a dozen times in a dozen different projects, assignments, projects, code that I put on GitHub, research, and it wasn't until I created this course where I actually had to explain the A-star search algorithm to people that I finally understood it. And so hopefully now that we've done everything that we have and we can frame the A-star search algorithm in this way, that you'll truly understand what's going on rather than just memorizing an algorithm. So A-star is by far the most well-known best first search heuristic search algorithm. And what's going to happen is we are going to evaluate a node using both G and H. And so the heuristic function is going to be f of n equal to G of n plus H of n. Okay? And so f of n is our estimate of the cheapest solution, total path, from a node n to the goal. But the important part here is, unlike greedy best first search that just says, let's go straight to where I think the goal is, this also takes into account how far we've gone. Right? To get the optimal path, you need to understand how far you've come so far. You can't just start going toward a goal. And so we're going to select a node from the open list with the minimum value of f of n. And the performance of A-star depends completely on the properties of the heuristic function. Right? Okay. So, and I'll talk about this a bit more at the end, if we set our heuristic to just be 0, for example. So our heuristic is always 0. F of n equals G of n. Oh, but the heuristic is 0, so it's just G of n. What algorithm have we looked at where f of n was equal to G of n? Does anyone remember that? I know no one's studying for the exam yet, but we have literally discussed an algorithm that was f of n equal to G of n. Uniform cost search. We select the minimum G of n from the open list, right? So if you set the heuristic to 0, A-star behaves identically to uniform cost search, which is Dijkstra's algorithm for a single goal. So if I had just said, here's the A-star search algorithm, would you be able to explain how it relates to maybe Dijkstra's algorithm or something like this? It's very hard to make that leap unless you've taken the journey that we've taken so far, right? And my goal, hopefully, is that you actually understand this stuff. So let's look at A-star with tree search. And again, tree search in the context of our textbook just means no closed list. Okay? Look at this. Have we seen this algorithm before? It's the exact same algorithm that we've looked at. It's just the only thing that's different is we take the minimum f value from the open list. Same algorithm. The only thing that changes is how we take a node from the open list. And so if we implement this as a priority queue, with the sorting function equal to f of n equal to G of n plus H of n. And for assignment 2, I'm actually going to give you a priority queue class. It's called a binary heap. It's pretty efficient. And you literally just pass in that sorting function. And then it's going to keep the minimum f of n accessible to you in constant time. And so this is a very efficient way to do this. But you don't need a priority queue. You could just have an array there and search through it for the minimum value of f of n. This is just sort of the best way to do it. So that's it. It's the same algorithm, just a different value that we search for on the open list. So let's look at A-star's performance. A-star using tree search is complete. That's good. So it will eventually search the entire tree. It will just search the parts where the heuristic is lower first. And A-star using the tree search algorithm is optimal if the heuristic is admissible. Okay, so that's why we cared about this admissibility property. Using a heuristic that is not admissible can, and usually does, produce non-optimal paths. So what this means is if you go back to my search program and you load up the A-star search algorithm and you use a 4-directional Manhattan distance with 8 directional movement, you can produce suboptimal paths. Okay? Now, maybe 90% of the paths that you try give you the optimal path, because it can still give you the optimal path, but it is not guaranteed to give you the optimal path. A star using graph search. Remember, graph search just means with the closed list. It can return suboptimal heuristics when we use an admissible heuristic. And so A star graph search using an admissible heuristic can discard an optimal path to a repeated state if it is not the first one that's generated during the search. So a later one that we find might be better. However, we can fix this by imposing a consistent heuristic. So this is another property of a heuristic that is a stronger property than just being admissible. So a consistent heuristic is also called a monotone heuristic, and this is the definition of a consistent heuristic. If the difference between so let's say we have 2 nodes, A and B, right, or 2 states, A and B. If we take the heuristic, which is the guess from how far I have left from A to the goal, and we take the difference between that heuristic with both nodes, that is going to be less than or equal to the cost of going from A to B. So in plain English, the change of the heuristic value between 2 states must be less than or equal to the actual cost of going between them. Okay? So let's look at an illustrated example of this, because this is everybody who teaches this says it is a difficult concept to understand, and to tell you the truth, I don't 110% visualize this in my head every time. But let's look at it. So this happens to be a triangle inequality. Has anyone ever seen the triangle inequality before? Basically, I'll show the triangle equality in a bit, but this is how I visualize this property. So we've got a node A and we've got a node B. This is our guess at how far we have left between node A and the goal. This is how far we think we have left between node B and the goal. And so what this is saying is that the difference between these two can never be more than the cost of actually going between them. Okay? This is the triangle equality. It's basically saying that one side of a triangle can never be bigger than the other 2 sides. Right? That's what the actual triangle inequality says. And if we want to apply this to the sort of grid world stuff that we're looking at, we can flatten out this triangle a little bit. We can arrange this triangle however we want. And so, for example, if we want to consider a straight line, which I will in a second, we can arrange it like this. So the difference between the heuristic guess between A and the goal and B and the goal is never going to be more than the actual cost of going between A and B. And like I said, this is equivalent to the triangle inequality. But remember, these are not the actual distances between these nodes and the goal, because that's a given. Right? The actual distance, that's a given. But this is our guess at the distances to the goal. And so, let's look at it as a numerical example. If we have my guess at going between A and G, okay, so I'm at node A, I think there's 10 left to the goal. Now I move 3 steps to get to another node, but I think there's only 5 left to get to the goal from that one. How is that logically consistent, right? So this is an inconsistent heuristic. Why? Because the difference between the heuristic values of these 2 nodes is 5, but the cost to travel between them is only 3. Okay, so this is an example of inconsistency. And I'll show in a second, but in practice, if you have a mathematical heuristic function that is not just arbitrarily chosen like this, if you come up with an admissible heuristic, the vast majority of the time, it's also going to be consistent. Okay? So it's actually very difficult to come up with an admissible heuristic that is not consistent, that is not some arbitrary label of things. So I came up with this last night, and it's just my intuitive, this is not a mathematical proof, but it is a sort of intuitive proof of why, if we have 4-directional movement, why would the Manhattan distance be considered a consistent heuristic? All right, let's take this example. So let's say I have the simplest possible case where node A and node B are actually the same state. Okay, so they're the same state. So that means that the cost of going from A to B is 0, and the difference between their heuristics is also 0, right? So this satisfies the consistent property. Now, here, when we move B, so we're going to keep A at the same place, but we're going to move B 1 in some direction. So we're going to move it away. When we move B, the cost to go from A to B is going to increase by 1. We're going to move it away from A. But depending on if we move it toward the goal or away from the goal, the difference in their heuristic value is going to go up by a maximum of 1, but it could go down, right? So let's have a look. If we move B up, its distance from A is 1. But the most that its heuristic toward the goal could have differed is 1. And it actually does differ by 1 because we have to make one down movement before we go over. Okay, let's look at another example. Let's move B again. Its distance from A is now 2, but because we moved it closer to the goal, it was that other case where the difference in heuristics now actually goes down. It's the difference in heuristics. Okay? So these actually have the same heuristic value now. See that? So they're both 6. So when we move it away from A, when we move it away from A, the cost from A is going up by 1, but the heuristic is either going up by 1 or going down. And if that's the case, then the cost will always be bigger than the difference in heuristics. Okay, so let's look at one more example. If we move it away like this, so the cost is 2, but the difference between the heuristics is only 2. And if we do the other example where we actually put B on the other side here, right? If we have B on the other side, this is actually the best case for this inequality, because the difference between A and B is maximized, but the difference between their heuristics is actually pretty small, right? So the cost to go to B is 8. It's very far away, but B is actually pretty close to the goal. So it's this. And sort of the worst case that we could think of is when B has to go in this sort of staircase pattern to get to the goal. But look, so this is the staircase pattern, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? But this is 6 away, and so 12 minus 6 is 6, and the cost to go from A to B is 6. So this is sort of how I visually interpret this and how I intuitively look at this, at least for the Manhattan distance. I hope that makes it a little bit easier to understand, but I have never seen a mathematical proof of the Manhattan distance. Maybe I'll find one someday and put it on the slides. So, a consistent heuristic. Every consistent heuristic is also admissible, right? Not every admissible heuristic is consistent, but every consistent heuristic is admissible. So if we had this like Venn diagram of all admissible heuristics, then consistent heuristics would be a subset of that. In practice, it is hard to construct an admissible heuristic that isn't consistent. If h of n is consistent, this means that the values of f of n along any path are non-decreasing. So the sequence of nodes expanded by A star using graph search is non-decreasing in f of n. That means that the first goal node that we select for expansion is optimal. So if our costs are non-decreasing, right? So the sequence of nodes expanded by f of n is non-decreasing order of f of n. It means we'll always be searching one that's the same or bigger, right? So we're ensured that if we had found one that wasn't optimal, we would have found it before. So that's a contradiction, right? So this is sort of the proof that A star using graph search is optimal if h of n is consistent. And this is not guaranteed if we only use an admissible heuristic. Okay, so we need a consistent heuristic. So this is A star tree search where we don't have a closed list. This is optimal if it's admissible. And this is with a closed list, optimal if h of n is consistent. So this is the same algorithm, just selecting a different node from the open list. So this is what we do for A star. This is uniform cost search, right? Instead of selecting minimum F, we take the minimum G. This is BeFS. We just take the first thing from the open list instead. This is DFS. We take the last thing from the open list instead. Yeah, so same algorithm, just choosing from the open list differently. Let's talk about a couple of small optimizations because I'm going to show them. I'm going to go through a time-consuming example, like an illustrated example of an A-star search to really drive it home into your head what's going on. But in that example, I'm going to show some of these optimizations. Here's the first optimization. If a node, so as we generate children, okay, so down here, C is the child that we've generated. So we're looping over the legal actions, adding them to the current state. Now we have a child. If a node N is in the open list with the same state as this child, and its g-cost is less than the child's g-cost, continue. What does this mean? Well, in plain old English, it says if we already have a node in the open list that represents the same state, and the path to that state is shorter, why would I even bother adding this one to the open list, right? If that one is there, and the cost to get to that chart is like, you know, if it's this sort of straight path, and now later on, I'm looking at the path where I go all the way around to that, why would I add that to the open list, right? It's never going to be a better path. Now, if you don't have this optimization, you are still going to get the same answer. But what this will do is it'll just save some memory in the open list. Okay, so this is a memory-saving device, and because I'm going to be showing things in slides, I need a memory-saving device so the open list doesn't get bigger than the slide. Okay? But keep in mind that what this does is it involves finding a state, or finding a node in the open list with the same state. And there's always trade-offs in computer science. This will save memory, but it will take time. How are you storing the open list? If it's a priority queue, well, priority queues don't let you just arbitrarily look up some value in constant time. So only do this if it is efficient to do so, right? That is a memory optimization, but it will never save you time. It will only save you memory, okay? Here's one that will save you time and memory. Or actually, no, this will just save you memory as well. But okay, there's a non-trivial cost associated with adding something to the open list, and so if the cost of adding something to the open list is greater than the cost of checking the open list, then it will save you time. So I apologize for saying it won't save you time. Here's another thing. If we generate a child, and I've already talked about this for the assignment, if that child's state is already in the closed list, then just continue. Don't add this to the open list. Why? Because if we add something to the open list that's already in the closed list, as soon as we take it from the open list, we're going to check if it's in the closed list, so just save us the time in the first place and don't add it to the open list. So both of these are memory optimizations, and they really help when I go to do these slides. All right, A-star graph search performance. Assuming we are using a consistent heuristic, let C-star be the optimal solution path cost. A-star is going to expand all nodes with f of n less than C-star. So what this means is that A-star is literally going to check every possible path that is less than the optimal path. But because of that, the next thing that it finds is the optimal path. So it is never going to expand any node that has a suboptimal path. Right? Suboptimal meaning longer than the optimal in this case. So it is never going to expand any node with f of n greater than C-star. So this means that A-star is optimally efficient for a given h of n. And it is not very often that we can say that something is optimally efficient. Like we have found the best algorithm, right? So no other algorithm is guaranteed to expand fewer nodes than A-star. Why? Because if it didn't expand every single path that was less than the cost of the optimal path, it may have missed the optimal path, right? So A-star is the one that expands the fewest amount of nodes and still guarantees us the fact that we know that it's the optimal path. So any algorithm not expanding all nodes with f of n less than c star risks missing the optimal path. So some of the pros of A star with a closed list is that, and a consistent heuristic, is that A star is complete, so meaning it will find a path if one exists. A star is optimal, meaning it will find the optimal path. And A star is optimally efficient for a given h of n. That's pretty good properties to have. That's why it's such a famous algorithm. However, the number of nodes searched can still be exponential in the length of the solution. And so for many large environments, A star is much better than, say, BeFS, but it can still be infeasible in the amount of time and memory. Okay? So your memory may just blow up. Okay? So it's still an exponential search algorithm, even though we have these nice properties. So what I'm going to do now is I am going to go through a meticulously crafted A star example. And I haven't found any errors in it in the last 5 years. So if you find any errors in these slides, please check my math as you're studying and tell me if you find any errors. I'm the type of person who wants to find errors so that I can correct them. So here's what this is. Up in the top left, we have a sample environment. We have a starting state up here. The open list is going to be in yellow, just like our assignment. We can path find between all of these light gray nodes. The dark gray nodes are a wall, so we cannot move to these. And our goal is to get to G down here. And we have octile movement. Down here, I have a shorthand version of the A star search algorithm. So while the open list isn't empty, we're going to choose the minimum f value from the open list. If that is the goal, then we return the path. If it's not the goal, if the state is in the closed list, then we don't need to continue with this one. If it's not in the closed list, then we add it to the closed list. Then, for every legal child of this node, if that state is in the closed list, don't add it to the open list. If that state, if the child's state exists in the open list with a lesser G value, then don't add it to the open list. That's that memory optimization. Otherwise, if it's not in the closed list and a better path isn't already in the open list, then add it to the open list. Okay, so that's the A star search algorithm in a nutshell. And for our assignments, we are using a cardinal action cost of 100 and a diagonal action cost of 141. Up here is where I'm going to show the open list, and over here I'm showing the states of the closed list. So the very first thing we do is, well, the very first thing we did was our root node is added to the open list. And so right now we have one node on the open list, and I'll explain what these are now. So the ID of the node, that's just, I'm going to give every node an increasing integer identifier just so I can say, okay, this was node 1, this was node 2, this was node 3. This is the state of the node. So currently this is state 0, 0. This is the G cost of that node. So since we haven't taken any actions to get here, the G cost is 0. H is the diagonal Manhattan distance guess at how far we have left to go toward the goal. So this is 141 plus 141 plus 141 plus 100, which I hope is 523. The f value is G plus H, and that's going to be whenever we take a node from the open list, we are going to select the minimum f value. And the action that we got here, that could be null, that could be 0, doesn't matter. I just put it up as -1, because actually that's a diagonal action, so maybe that should be null. But we didn't take an action to get here, and there is no parent pointer, right? Because this has no parent. So the action and the parent, for all intents and purposes, are null. So the first thing we do by our algorithm is we look through the open list and we select the minimum one, right? That's really easy because there's only one. So we've selected it. It is not in the closed list, so we add it to the closed list. So now we've marked this one as red, and we've put that state into the closed list. Okay? And there's nothing in the open list, so none of these. Oh, sorry. Now what I do is I go to look at all the children of this node. So the first child, is that a question or are you just scratching? Okay. Okay, yeah, I just saw your hand up. So now we're going to look at the children. So this is the first child of this node right here. The G cost of this child is 100. So what we do, we say, okay, is that state in the closed list? No, it's not. Keep going. Is there a node in the open list with a better G cost with the same state? Nope. So we add this to the open list. Okay? And so we can see here that this is state 1, 0. We have taken action move right, which has cost 100. The H of this is 141 plus 141 plus 100 plus 100. So that's 482. So the F cost of this one is 582. The action that we took to get there is 1, 0, and the parent pointer is node 0. All right. Now we look at the next one. And now that I've done a couple of examples, I won't be so verbose with the next ones. Here's the next one. So this is not in the closed list, and it's not in the open list. So we add it to the open list, and we calculate all of its properties. Here's the next one. It is not in the closed list, and it's not in the open list. So we calculate all of its properties. Okay? So now what we have after this iteration of the while loop, here is the state of our A-star search. We have one state in the closed list, and we have 3 nodes in the open list. So the next thing we have to do is go back to the top, and we're going to select the node that has the minimum F value. Okay, so we'll do that. And it turns out to be this one. Oh, look, there's a tie. What do we do in the case of a tie? I'll talk about that a little bit later, but for now, we're just going to choose the first one, because it doesn't really matter. No matter which one we take, we're going to find an optimal path, but let's just take the one on top first. So we remove that from the open list, and since it wasn't in the closed list, we keep going, and we add it to the closed list. So now 1, 1 is in the closed list. Okay? Now, a really interesting property that we can see is that whenever, remember that property of how we always expand all the nodes that have a lesser path to the goal node? That also works for every node that we take off of the open list. So every time we take a node off of the open list that isn't in the closed list already, that means we have now found the optimal path from the start to that node. Right? So if I ever want to know the optimal path from this node to the start node, that's just this. So whenever I pop a node off the open list with A star, I have found the optimal path to that node. And if that node happens to be the goal node, then we've found the optimal path to the goal. So that's just a fun aside that you can use for different optimizations in other domains. So now we have this one, and we are going to look at its children. Okay, so we're going to go in clockwise fashion, looking at the children. Here's the first child in the top left. Oh, look, that one's in the closed list, so we can skip it. Right? Here's a child. Here's the first example. So this is not in the closed list, but look at this. That state, 1, 0, is in the open list. And when we got to that state in the open list before, what did we do? Well, we only went to the right. So the G cost of the version that exists is 100, but the G cost of this one is 241. So I'm basically saying, okay, this is not in the closed list, so I can't discard it outright, but if I already have a better path to that node in the open list, why would I add this one? If I do add it, it's fine. It'll just never be expanded. But this is that memory optimization, and you can see that I need all the memory optimizations I can get with this slide. So this is the first time that that happens. That is that green check down there, so I've color-coded that. So I'm not going to add that to the open list, even though it's not in the closed list. But for assignment 2, do not do that optimization right away. Do not live or die by that optimization, trust me. Get everything working without that optimization, and later, if you want to try that optimization, do it. But that is absolutely not necessary to get 100% on assignment 2. All right, next one. There's a new child. And it's not on the open list or the closed list, so we add it to the open list. And of course, this is now, okay, diagonal down, diagonal up, so that's 282, 141 plus 141. Next child. Well, we're going to skip over this one and this one because these are not legal actions, right, because you can't move into the wall. So the next one is down here, not on the open or closed list, so create it, add it to the open list. This one, not on the open or closed list, so create it and add it to the open list. And this one, same thing as the one that was above it. We already have a path to that one that's better, so skip adding that one to the open list. Now, here's where we are after 2 iterations of the A-star search algorithm. And you can see, we're heading down into this concave structure, right? But Let's see where we go. Next, remove the minimum f value from the open list. It happens to be this one. Okay, well, there's two, but we're going to take the first one. Let's do the same thing. So we add it to the closed list. We look up. Okay, that one's already in the closed list. Don't add that one. This is the same thing. We have a better version in the open list already. Don't look at that one. This one is already in the closed list, so I can skip it. This one is already in the open list. So this is 1, 2, and it says less than or equal to, right? Even if it's equal to it, then I'll just take that path. I don't need to add this to the open list because it'll be the same length path. So I can skip that one. This one, oh, look at this. This is an interesting case. Now, this is a case where it's in the open list, but this new version is better than the one that was in the open list. Okay, so now I have a path that's better. Look at this. So this is 0, 2. If I look here, 0, 2 is already in the open list, and it has a G cost of 282. But this one has a G cost of 200. So what I'm doing for, oh my God, look outside. That's crazy. Yeah, okay, I'll get you out of here soon. I'm going to have my Discord, I'm going to have office hours on Discord today because I don't want anyone to have to stay around for 2 hours in this. All right, so in this case, and really only for the slides, because this is what I'm about to show you is a very difficult optimization to do in practice, okay? But what we're going to say is if we have a new version that's better than the old version, delete the old version from the open list. But if you're using something like a priority queue, then deleting something from the priority queue causes a rebalance to happen, and that can be a very expensive operation. Okay? So in practice, I always encourage people to experiment with these algorithms, but don't do this for the assignment. It'll cause you more headache than it's worth. Again, this is a slide memory optimization. Okay? So again, what I did there was that I found a new path to a node that had the same state that was already in the open list, and the new path was better. So I'm just deleting the old one, because if we ever go through this node for the optimal path, we will never expand this. This one will just never be expanded, so it's a waste to have it there. But like I said, in practice, that is a difficult optimization to perform efficiently, so don't worry about it. Okay, third iteration. Now I'm going to get a little bit faster with the explanations, especially given the weather outside. All right, so here we go. This is the thing with the lowest f value. Take it, put it in the closed list because it's not in the closed list. Now let's look at its children. This is one of those cases where there's already a better version in the open list, so I skip it, and I'm not going to do the whole thing where I say, okay, this is in the closed list. The other children are either in the closed list or they're walls, right? You get that by now. Let's look at the next one. Here's the minimum f value. Look at its children. This is another case where I have a version in the open list that's worse. So I'm just going to overwrite it with the new version. Again, don't do that in practice. I'm just doing it for your benefit with these slides. So that's what we did there. Choose the next f. This one has the best f. You may say, well, that's not very intuitive that it's down there. But remember, it's using this heuristic that can go through walls, right? So this is the minimum f value. We check that one. All of its children are in the closed list, so that's obviously, we're not going to do anything there. Now we have a single node in the open list, so let's add its children. So this one is not in the closed or open list. This one is not in the closed or open list. Now we choose the minimum f. It's this one. We check its children. This one, this is a worse path than the one that already exists in the open list, so we don't add that one. That's that green optimization. Then we add this one. Next, and you can see from here on out, we're just going toward the goal. Now, here, we've selected this one, and we're adding the children, right? Look, I've generated a child. That is the goal node. But here is why we do not stop the search at the time of child generation. Why? Remember up here? Remember how the first time I generated this node, I went down right, then up right? The first time I saw that node as a child, I was generating a bad path toward it. It's not until we take it from the open list that I can guarantee that I've found the optimal path toward it. So do not check for the goal at the time that you generate the child. What is going on outside? How is it sunny and a blizzard. Anyway, welcome to Newfoundland. So only at this point, now this is another child that I generate here, and then only at this point where I take this one that happens to be the goal from the open list. Now the goal has been expanded, right? The goal has been taken from the open list. Now I can go through the parent pointers and find the path to the goal. All right, and we know how to do that now. The last thing I'm going to tell you for this lecture, and then I'll show a little bit of a demo, is called weighted A star. So this is another algorithm that puts a little spin on the A star search algorithm. And it's really, really cool, actually. So we can tweak the performance of A star by adding a weight parameter that I'm going to call W. That's what most people call it. And then what we're going to do is, instead of just taking f of n, or the minimum value of f of n as g of n plus h of n, I'm going to weight the heuristic value. Okay, what does that mean? As we set the weight greater than 1, so if this weight is equal to 1, it's just the same as A star. If the weight is greater than 1, then A star favors going in the direction of the heuristic more and more. Right? So as W increases, then the heuristic becomes more and more important to this formula. As the weight gets less than 1, and we only go down to 0, we don't go negative, then A star trusts the heuristic less and less. So what happens as W approaches 0 or infinity? Well, let's have a look. So here's A star. F of n is equal to g of n plus h of n. I've intentionally put some spaces here so that I can put some w's in. What is uniform cost search? It's f of n equal to g of n plus 0, right? What is greedy best first search? It's f of n equals 0 plus h of n. Weighted A star puts a weighting on the heuristic. So this is A star when we have this equal to 1, right? As our weight approaches 0, weighted A star approaches the behavior of uniform cost search. As our weight approaches infinity, it approaches the behavior of greedy best first search. So this is a great exam question, because this really now starts to test the understanding of the relationship between these search algorithms. And you may, hopefully now you're starting to see, oh, there was a point to go through all of this rather than just give you 10 algorithms and ask you to regurgitate them. So let's really quickly go back to the search demo and show you this in practice. Let's go to a more interesting example. So let's first start off with the A star search algorithm. So let's search from here to here. And let's speed this up a bit. Here's the A star search algorithm going from there to there. The reason it's not going straight to the goal is because it is considering how far we've come so far. Right? So this is what it's doing. It's getting caught in a bunch of these concave bits, but it has to. Right? It has to check those because it thinks that that's the quickest direction. Oh, now, as soon as the current node is within line of sight to the goal, that's when it finds the quickest thing. But someone remember, oh, I got to click rerun path. 1 second, instant path, rerun. Okay. The path cost there is 17,321. 17,321. I'm just going to type that up there. Now, we're going to use weighted A star. Okay, weighted A star with a 1 times heuristic is obviously identical, right? It's the same algorithm because it's g of n plus h of n. Let's gradually increase the heuristic. Okay, we've searched fewer nodes and we got the same path cost. But is our heuristic now admissible or consistent? Well, if we're multiplying it by 1.1, it could be bigger. So it's no longer consistent. So we're no longer guaranteed to find the optimal path. Let's multiply it by a bit more. Way fewer nodes, but look, now the path cost is bigger. Let's see where it's suboptimal. Can we see it here anywhere? Somewhere, yeah, look, it went like down into here and then back when it didn't have to, right? The non-consistency of the heuristic now, which is 1.5 times h of n, is no longer guaranteed to find optimal paths. Let's keep going. 2 times the heuristic. 4 times the heuristic. The path cost is getting worse and worse because we're getting further from optimality, but it is trusting the heuristic more and more. So the amount of nodes that we search, look, the closed list size is now 564. What it was with 1 times heuristic, 6,000. So A star searched more than 10 times the nodes, like 12 times the nodes as this. But look, if we keep putting the heuristic up and up and up to infinity, we get greedy best first search, and this is what greedy best first search looks like. This is like visual, not proof, but intuitive proof that yes, it is approaching that. Now, unfortunately, I do not have the option in this UI to move the heuristic down and down, but if I did, and then I got the heuristic all the way down to 0, then we would have uniform cost search, and it would search even more, because it doesn't have that heuristic guiding us toward the goal. And actually, a really cool thing about uniform cost search is that since it's always just taking the minimum G cost, when you have octile movement, it's basically searching out in a circle. So if you just expand a circle, it's almost like a mushroom growing, right, or fungus growing, right, if you're from biology. And so this, it has nothing guiding it toward the goal. So usually, uniform cost search, yes, it is guaranteed to be optimal, but it has nothing guiding us toward the goal. So it's typically going to be searching more nodes than A star. Greedy best first search, with that weight pumped up to infinity, right, is going to go toward the goal a bit faster, but we are no longer consistent, and so we may not guarantee optimality. And there are proofs out there, which I'm not going to go into, but basically, if we have a 2 times heuristic, or a 2 times weight on weighted A star with the heuristic, we are guaranteed that the path that we find will be no longer than 2 times the optimal path. Okay, because that's the worst case that it could be. In practice, with normal maps, you will not get anywhere near double the optimal path. You'll actually usually get, pretty close to it with far fewer nodes searched. So for example, if you have a video game, right, now you want to have a pathfinding algorithm in your video game, you can use weighted A star. And you may say, okay, do I really care about the path being optimal, or do I want it to run 20 times as fast? So you can play around with this weight, give it to your testers, and see, right? Now, in actual fact, there are algorithms out there that are way faster than A star when you have grids like this. So typically you'll use something like jump point search, which I may or may not get into. But there are grid-specific algorithms that are faster than A star. But for a general graph-based search, nothing can beat A star and still be optimal. So hopefully that gives you like a good explanation of what A star is, because I had implemented that algorithm so many times before I really understood what was going on. And I think relating it to all these other algorithms like this really does give it an intuitive feel.